In this video, we're going to talk about a concept called implicit differentiation. This concept is extremely useful when you aren't working with a function that you can solve for y. For example, you see this problem here. We have y squared equals x. If we were to solve for y, we would be taking the square root and having a plus or minus to deal with. It's much easier to work with it as is and taking the derivative. So all the problems we've done before, up until now, have been a situation where you had y equals a function of x. Maybe some other variable besides x, but it was one variable on each side of the equal sign. So we were able to differentiate it using the techniques we've discussed. Now, all those techniques are going to come into play here when we do implicit differentiation, but there's a couple of new things that you're going to have to watch out for. So let's read the directions. Number one, differentiate both sides of the equation with respect to x. In the past, we've just written dy dx on one side and taken the derivative of the other. Just the process, though, of writing dy dx on the left-hand side, technically, that's taking the derivative, but it's the derivative of y with respect to x. So we actually wrote down dy dx. On the other side of the equation, we had all x's. So we would have ended up with a function of just x's over here. Okay. Now, we're going to have a situation where maybe it's not y by itself on the left. Maybe there's a y on the left and the right. Maybe there's x's and y's mixed up together in the equation. It could be all sorts of things. So this technique, implicit differentiation, allows us to tackle those more challenging equations. There are many equations out there that are interesting for studies that really don't lend themselves to being solved for y by itself. So first of all, you're going to differentiate both sides of the equation. Technically, we've been doing that, but it's going to be a little different now. And we're going to do it with respect to x. So on the bottom will be dx. And you're going to treat y as a differentiable function of x. I'll show you what it means. Number two, collect the terms with dy dx on one side. So you're basically going to solve for dy dx. And that way, you're going to have the derivative of y with respect to x. The only weird thing now is that dy dx is going to equal something that could involve x's and y's. I'm going to show you some examples. So here we have the equation y squared equals x. Notation-wise, what we're going to do is we're going to write d dx on both sides. What this means is we are taking the derivative of the equation. I'm writing it on both sides because, like I said, we have to take the derivative of both sides. It's not just y by itself on the left. So, what is the derivative of y squared with respect to x? Well, to start off, just use your traditional derivative rules. What's the derivative of y squared? What rule would you use? You should be thinking, well, this is a power rule. So the power rule says we bring the 2 down, and then we have y to the first power. You don't have to write the 1 if you don't want to. Now, you're not done. Normally, we would be done, but we are dealing with the variable y, and we're taking the derivative with respect to x. So we actually have to consider this as somewhat of a chain rule. We've done the power, we've done the 2 down, 1 power less, but now we have to take the derivative of y itself. So we're going to multiply times the derivative of the y with respect to x. Isn't that kind of weird? I agree. Now, let me show you on the other side why we're having that end up there, whereas normally we wouldn't. On the right-hand side, the derivative of x with respect to x. Now, you all know that that's 1, but why? Let me show you. So this is dx on the right. Wait a second. On this fraction, the top and the bottom match, whereas on this fraction, they're different variables. So on the right-hand side, these two cancel out and just leave us with the 1 that we're used to. On the left, we can't cancel because they're different variables. Dy dx does not reduce. So that's why we're stuck with 2y dy dx equals 1. In general, when you're doing implicit differentiation, anytime you take the derivative involving the y, you're going to end up with dy dx. If you're not taking the derivative of the y, you don't need it. For example, on the right here, there was no derivative of y on the right, so you don't need a dy dx. So our last step in this problem is to get to dy dx by itself. Well, that's just multiplying by 2y. So how do we move the 2y over? Divide by 2y, and your dy dx is equal to 1 over 2y. So again, notice our derivative of y with respect to x is a function, but it's a function of y in this case. Sometimes it'll be just x's, sometimes just y, times it'll be a combination of the two. We'll look at some more examples as we go through. All right, here's it. Oh, look at this one. Can you imagine trying to solve this equation for y? That would be a nightmare. Actually, it's probably impossible. So what we're going to have to do to find the dy dx, we're going to have to take the derivative using implicit. So let me copy it down, and we're going to use the same steps as before. I'm going to put xy in parentheses because all of that's inside of cosine. So again, we're going to write what we're going to do. We're going to take the derivative with respect to x of the left and the derivative with respect to x of the right. Okay? On the left, this is very similar to what we just did. So the derivative of y squared, the 2 comes down, the y has a new power of 1, times the derivative of the y itself, the derivative of the inside. So remember, this is chain rule, where we don't end up with just a 1 because it's not an x, it's a y. So dy dx equals. On the right-hand side, well, we're going to do the two terms separately. The first term is just a function of x. So the derivative with respect to x, this is what you're traditionally used to. So 2 comes down, x to the first power. You can write dx dx, but it's just 1. Plus, let's do the second term's derivative. So in this case, what rule do we need? This is going to be chain rule. So our outside function is cosine, means outside. xy is our inside. What is that? Well, that's going to be a product. Well, we'll worry about that when we take the derivative of the inside. Let's start with the first step. Chain rule says you take the derivative of the outside. Derivative of cosine, negative sign. So let me fix my sign here. Negative sign. Chain rule says the inside stays the same, but you're not done. Now you need the derivative of the inside. Oh boy, how do we do the derivative of this? Well, this is x times y. So we're going to need a product rule here. So let's just take that over to the side here and work that out. So we have an x times y, and we're going to take the derivative of that with respect to x. So we're going to need u prime v plus u v prime. Well, let's let u equal the x, and let's let v equal the y. So then the derivative of x with respect to x, what is that? 1. Be careful, the derivative of y with respect to x, well, that's your dy dx. Okay? Product rules, we multiply 1 times y, x times dy dx. So we end up with y plus x times dy dx. All right, this goes over here. That's the derivative of the inside. So this is a really, really big hurdle for a lot of students to recognize that this is a product rule. A lot of students don't get that right. So make sure you understand all of this is the derivative because we had to use the product rule. All right, so we're almost done, but not quite because they want us to actually find dy dx. Well, dy dx is kind of sort of hiding from us, but it's visible now. It's right here, dy dx and dy dx. We got to get those two by itself. Let me make some more room. Pretty sure I'm going to need it. Whoops. There we go. All right, so to get dy dx by itself, we got to clean this up. So let's just rewrite 2y dy dx equals 2x. Now this negative sign of xy could distribute to the parentheses. So let's do that. So negative sign of xy times a y. I'm going to put that y in front. Minus sign of xy multiplied by x dy dx. I'm going to put those in front. I just like to put them in front so there's no confusion about who is inside the sign function. All right, those are all of our terms. Well, we can still see dy dx, but we don't have those parentheses blocking our way anymore. So how are we going to get dy dx by itself? First, we got to gather them to the same side. So we'll keep the term on the left that's there already. And we're going to bring the other dy dx term around. So he becomes positive x dy dx times sine of xy equals the other two terms, 2x minus y sine of xy. We're getting really close here. Here's your dy dx's. The problem is we have two of them. How do we solve for dy dx if there are two of them? Do you remember the algebra trick that you need here? Factor out dy dx from both terms. What's left? First term is just 2y plus an x sine of xy equals 2x minus y sine of xy. We are almost there. We just need dy dx by itself. So dy dx is multiplying by the parenthesis. So to get rid of the parenthesis, we divide. Both sides. And there you have it. This you cannot simplify. Sometimes you can, but in this case we cannot. So dy dx, what we were looking for originally, is equal to this function on the right. Notice this is a function that does no dy dx's because we had to solve for that. It's on dy dx is only on the left. On the right we have x's and y's. There are multiple terms. Some terms have x, some have y, some have both. Some have both multiple times. That is a crazy looking derivative, but that is the derivative, right? So you can see how implicit allows us to find the derivative without solving for the y. Okay, now it's your turn. I want you to pause the video and I want you to try this one. It's going to be your first try, so it might be messy, it might be a little rough, but try it. Write d dx on both sides and try and use your derivative rules. Remember, if y is involved in the derivative, you need a dy dx there. So pause the video and come back. All right, hopefully you paused it, hopefully you gave it a shot. Let's see how close you got. So watch, well, do it with me. X cubed plus y cubed equals 12xy. So I'm just copying it down so that I can write the, so that I can write the d dx on both sides. Nice and clear. So I'm saying I'm going to take the derivative with respect to the x variable. So anytime I have a y involved, I'm going to have a dy dx. All right, first term, x cubed. Well, there's no y, so that's just normal. 3x squared plus, there's a y involved, but it's still the same rules. Just at the end, you've got to take the derivative of the y itself. So 3y squared times the derivative of the inside, the y. So dy dx equals, all right, now here we go. We have here three things multiplying together, but this 12 is just a constant multiple. So what can we do with a constant multiple? Leave it alone, let him chill out while you worry about the rest. So 12 times the derivative of xy. What do we need to take this derivative? Didn't we just do that? Well, let's practice it again. This is a product rule. So if we want to take the derivative of xy, this is u prime v plus u v prime. So if u is x and v is y, the derivative of u, we're doing the derivative with respect to x, so that's 1. The v prime, the derivative of y with respect to x, we have to literally write dy dx. Put it together. So 1 times y, or y, plus x times dy dx. So we plug that in. So we have y plus x dy dx for our product rule on the right. And that's it, the derivative is done. But you have to find dy dx. You gotta get dy dx by itself. To do that, you've got to get rid of these extra parentheses. So distribute your 12. If you'd rather divide by it, you could, but you're going to end up with fractions. So I'd rather avoid the fractions. All right, so if we distribute the 12 and bring everything down, so 12y plus 12x dy dx. Now you're trying to get these dy dx's by themselves, so you have to get them together. So let's keep 3y squared dy dx. Let's bring around the other dy dx, so minus 12x dy dx equals, we already have a 12y on the right. Don't forget to bring your 3x around. So he becomes negative 3x squared. Almost there. Make some more room. we have two terms with dy dx. So what did we do to get dy dx by itself? Hopefully you remember we factored out dy dx. If you guys got this far on your try by yourself, great job. If not, that's okay. This is something new to most of you, and you just need to see some more examples to get used to the process. Finally, divide by the parentheses. So dy dx will be by itself equal to what's on the right divided by the parentheses. Now you should ask yourself if you can reduce this, which if you look at it, you can. Every single term is divisible by 3. So if we reduce by 3, we get 4, 1, 1, 4. So we end up with y minus x squared, 4y minus x squared over y squared minus 4x. Now these can't be factored. If they could, you'd factor reduce as appropriately, but we can't. So this is our dy dx. Again, it's a function of x's and y's. All right. Again, if I were you, I would pause the video and give it a shot on your own before you watch me do it. So pause the video and come back. All right, so hopefully you tried it. Let me copy the problem down. So we're going to take the derivative with respect to x on both sides. Oh boy, look what's happening on the left. That's craziness. So on the left, first of all, the 2 and the 3 are constant multiples. So they can just chill out while we take the derivative of what's next to them. What's next to them, though, is x squared y. That's a product. And over here we have an xy squared, which is also a product. So we're going to have two product rules on the left. That's going to be fun. You can do it. Keep the 2, multiply by the product rule, plus keep the 3, multiply by the product rule, equals. You know what? The right-hand side is a relief. Let's go ahead and do the right hand. We have the derivative of a constant. Doesn't matter what you're with respect to. Derivative of a constant is always 0. Beautiful. All right, product rule. So I wrote 2 on the mount. This time I'm actually not going to write out the whole step. I'm just going to do it in my head. So u prime v plus u v prime. So we have our u, and we have our v. So the derivative of x squared, 2x, times the original v, plus u, the original u, times the derivative of v. Now remember, v is the y, and we're doing with respect to x. So we have to write dy dx. Okay? Let's do the other one. So we have u is going to be our x, v is going to be our y squared. So u prime v plus u v prime. So the derivative of x, that's just 1, times the original v plus the original u, which is x, times v's derivative. All right, how do we take the derivative of y squared with respect to x? Do your normal power rule. So y squared is 2y, but then you need the derivative of y with respect to its x. All right? That's it. Derivative is done. All you have to do now is simplify so that you can find dy dx. Get it by itself. All right, to do that, distribute your 2 and distribute your 3. Clean them up. So we have 4xy plus 2x squared dy dx plus 3y squared plus 6, I'm going to reorder this, but xy then dy dx, all equals 0. If you got this far, you guys are doing great. If you didn't get this far, be patient with yourself. It takes practice. That's why I have lots of examples here. All right, so keep the dy dx terms on the left. So we have 2x squared dy dx and the 6xy dy dx. The other two terms, we're going to move to the other side of the equation. So they both become negative. So negative 4xy, negative 3y squared. Do you remember what we do next? You have dy dx in common, so we can factor that out. So we are left with 2x squared plus 6xy equals negative 4xy minus 3y squared. All right, more room. Long problems. So if we get dy dx by itself, we divide by the parentheses. So on the right we have the original right, negative 4xy minus 3y squared all over the parentheses. 2x squared plus 6xy. And there you go. That is your derivative. Okay, I have one more example. Again, please try it on your own and come back and watch. All right, so let's give this a shot. So again, we're going to do d dx, the derivative with respect to x to each side. Oh goodness, what are we going to have to do on the right-hand side? That's a quotient rule. But you know what the good news is? It's a quotient rule, but only x's are involved, so that really does help a lot. All right, so let's start with the left. 4y squared. Well, we know what to do with the 4, right? 4 chills out. The derivative of y squared with respect to x. Well, y squared becomes 2y, and then the derivative of y with respect to x. That's it on the left. Equals. On the right, there's nothing weird here. This is the normal quotient rule because it's just x's. So remember, the quotient rule is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So u is going to be 3x minus 2, the top, and v is going to be 3x plus 2, the bottom. Find the derivative. So that'd be 3, and the other one's also 3. And then we do the quotient rule. So u prime times v and u times v prime. So on the right-hand side, we have 3 times 3x plus 2 minus, we have a 3x minus 2 times a 3 over the bottom 3x plus 2 squared. All right, let's clean it up. So on the left, we have 8y dy dx. On the right, we have a mess. We got a lot of work to do. Not that bad. Distribute your 3. Now be careful. The second one here, you have a negative and a 3. So really, you have a negative 3 that you're distributing. So distribute 3, so 9x plus 6 minus 9x plus 6 all over the bottom squared. We can cancel out the 9x's, and the 6's can add together. So 8y dy dx equals 12 over 3x plus 2 squared. How do we get dy dx by itself? It's right here. We divide by the 8y. So we put 8y in the bottom. Well, now we have 12 and 8. Those can both reduce by 4, so we're left with a 3 and a 2. So dy dx all by itself on the left equals 3 over 3x plus 2 squared and 2y. Well, I like the 2 and y in front, but it really technically does not matter. And there you have it. That's your answer. So those were my examples of implicit differentiation. If you need more help, please reach out to me and let me know. These are fairly challenging, but they use all the same rules. The main difference is if you have a derivative involving a y, be sure to put dy dx. That's it. Good luck, study hard. I'll see you in the next video.